Okay, so the sampling distribution. What is a sampling distribution? Okay, so we defined three estimators. If we look at them here, the sample mean, the sample variance, and the difference between means. So these are functions that you're given particular samples, they will compute estimates for you. Okay, so the sampling distribution, right, here is the picture. Given a particular sample taken from the population, you compute an estimate. Now the sampling distribution, sorry for the scrolling, is what happens when you instead of inputting a particular sample, you input a random sample. Okay, so this is a theoretical concept. You can't actually in practice, like a random sample is a theoretical, it's a distribution of all possible samples you can obtain. So if you compute the estimator from a random sample, you get a random variable, and the distribution of that random variable is called the sampling distribution of G. Okay, we're focusing on 4 estimators, and these are their sampling distribution. So the mean, the sample mean, the sampling distribution of the mean is what you get if you compute the mean from a random sample. The sampling distribution of the variance is what you get if you compute the variance from a random sample. So the formulas are exactly the same as what we saw above, but now we're using capital letters. So it's not a particular x, it's the random variable x. Okay, so I get nothing new, mathematically speaking, but we're using capitals. Okay, so let's look at some graphs. Okay, I'm going to run this. So these are a bunch of functions that we'll learn about later on. We'll show what's going on here. But essentially, okay, here is sample. We choose the population, so we need a model for the population. We're going to use the simplest possible population, a standard normal random variable. Remember, so this looks like the bell curve. And here is 10 samples from that distribution. And the samples are of size 20. Okay, and we see them here. Let's plot it. Okay, so this graph contains the points. So these are the values from the first sample. The blue dots are the actual observations. And we've annotated with the diamond shape the mean we computed the mean from this sample. Okay, and as you can see, each sample has a different mean. And the distribution of these diamond shapes, right? You see that they're roughly around 0, but they vary. That's called the sampling distribution of the mean. Specifically, the sampling distribution of the mean from samples of size 20 from the distribution from the standard normal. Right? So this is the random variable. Okay, how many? We generated 10 of them. How many observations in each sample? 20. Okay, on the same graph, we've also computed the standard deviation. So if you take this sample, you compute its mean, you compute the average deviations from that mean, you get, this is one standard deviation away from the mean. That's what standard deviation means. Okay. This is where it gets interesting. So you take all these diamond shapes, okay, instead of just 10 samples, we're now generating 1,000 samples. Okay, so you get 1,000 diamonds similar to how we had 10 here. But now when you generate 1,000, you start to see the shape of the possible sample means you can obtain from the sampling distribution. So this is a simulation of the sampling distribution of the mean. Okay, now let's plot also the sampling distribution of the standard deviation. Okay, so we've computed 1,000 samples, and for each sample we computed the standard deviation, right? So these are the little bars here, right? The distance from here to here, the distance from here to here, the distance from here to here. It's symmetric, distance from here. Okay, and then we plot all of them. So the average distance from the mean seems to be around 1. But there you see there's a little curve. Okay, so this shape here is called the sampling distribution of the standard deviation. Okay, in the book I don't show the code at first. We'll show a lot of code later on, but this is the visual explanation of what a sampling distribution is. Okay, and note this is the sampling distribution of the mean, this is the sampling distribution of the standard deviation. Any estimator, we can obtain such a graph, generate thousands of samples, compute the estimate from each of the 1,000 samples, and plot the distribution of the estimates. Okay, here is a picture. What's going on? Remember the picture earlier, we computed the estimator from one particular sample. But now this is a capital X. We're computing the estimator from a random sample. So that's the sampling distribution. And it's a random variable, so it has a distribution, like you see here, like you see here. Okay? A little bit of vocabulary. The bias is a measure of are you accurate on average? Are you on target? Okay. An estimator. So imagine these are arrows hitting a target. So this is, you see, the variability that, in every sample, you're going to get a different estimate. And this is the best case scenario where you have a little bit of variability, but they're all roughly on target. And the biased estimate is one where, they're consistently off target. So that's called the biased estimate. On average, it's not hitting the bullseye. A high variance estimator, on average, it's hitting, the mean, but you see they're really spread out. So that's the variance of the estimator is how spread out the estimates are. Okay, and this is the worst case. They're off and they're spread out. The estimates are no good. And the way we measure the variance, so this is the variance, but it's more practical to take the square root of the variance, and that's called the standard error. Okay, so the standard error of the estimator G is the square root of the variance of the estimates. Yada, 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 terminology. Okay, so up until now, we talked about the sampling distribution as a mathematical definition, and that's one way to look at it. But the beauty of having Python on our side is that any quantity, like the concept of a sampling distribution, we can actually simulate it. How we're going to simulate it, as we saw earlier, is generate thousands of samples. Okay. And we can compute the estimates from each of the samples we generate. And then this is a list of observations from the sampling distribution. So if you plot a histogram of that, then you get a graph like this. Okay, so here I did it in the beginning of the book. I just show it visually, but now we can actually write the function that generates these plots. Okay, so let me run it so it's defined. So this function we'll use at least 10 times in the remainder of this notebook, so it's important to read it. So given the population random variable, so this describes the population, and the estimator, and the sample size. So you need to tell me how big are the samples. This function will generate 10,000 samples. Okay, so this is the for loop that generates 10,000. For each, so this is how you generate a random sample from this population, right? The sample size of n. Then you compute the estimator from that sample. So this should really be called estimate. And then we just collect a list of these observations here. I need to update the notebook because this is the better way to, so the estimates. Okay, let's see it in action. Okay, so this will be a running example. We'll see repeatedly the kombucha volume. So imagine a bottling, a factory where we're brewing kombucha, and we want to create 1 liter bottles. But because of the bubbles, sometimes you're going to get a little bit less volume and a little bit higher volume. So we want 1,000, so this is 1 liter, but there's some variability in the volumes of the kombucha. And this model here, the random variable k, describes how the volume on average you can expect from the variability of the volumes. Okay. So ideally we want all the bottles to contain 1 liter, but you see that it's possible there's a bottle that's 10 milliliters less or 10 milliliters more, and this is the variability. And here is so we're calling the function generate sampling distribution. We told it the random variable for the population, and we're asking it to generate the sampling distribution of the mean from samples of size 20. I didn't specify how many simulations to run, so it will use the default 10,000. And lo and behold, we get a graph. Notice the width here is smaller than the width here. So these are the sample means. This is the volumes in each bottle. This is the volume, the average volume in a sample of size 20. Okay, so K bar, right? K overline means the sample mean from a sample. Okay, and we see on average the sample mean is going to be very close to the population mean, but you see there's a variability. Okay, and remember the the standard error of an estimator is the standard deviation of this distribution. What is the width here? So we can calculate that. And yada yada. Okay. So in chapter 2, we learn about the central limit theorem. That tells you a formula for how the variability of the sample means. And the formula tells you that the standard error, so the variability of this distribution, is going to be equal to the standard deviation of the population divided by square root of the sample size. So let's take a look at that. So this is the simulation, and the standard deviation of the simulation is 99997. This is the standard deviation of the simulation, and the central limit theorem predicts that it will be 2.23, 2.2. So in both cases, we're pretty accurate. So this is going to be a theme that reappears many times in this notebook. So one direct approach using simulation, this is the real sampling distribution. You know, we actually generated 10,000 samples and we computed. And this here, the central limit theorem, is an approximation we obtained from a math equation. And in this case, we see that it's pretty close. Like the prediction from the central limit theorem is very close to the observed, the simulated standard deviation, the standard error. Okay. Now, the same exact thing, but now we use the variance as the estimate. Okay, so we generated 10,000 samples from the kombucha population, computed the variance from each sample, and this is what you get. So on average, the variance is going to be around here. But you see, sometimes you generate a sample, it can be have a very high variance, sometimes it can have a low variance. So that's why we need a concept. You know, when you want to know what's the variance of a sample, this is the variances you can expect from random samples. Okay, and we see that the mean of this distribution is roughly equal to the population variance. Okay, so why is this important? Is because every time you compute an estimate based on a particular sample, you're going to get one number. And we want to know, when you report that number, you want to know the uncertainty, and that's what the sampling distribution tells you, right? So on average, the estimates you compute, the sample variance you compute, they will vary. There will be a distribution of them. And this is what tells you the uncertainty in your estimates. Okay, so all of these examples we generated here were in a scenario where we know the population. So that's why we were able to generate the simulation and know, compare it with formulas. In the next video, we're going to talk about how to approximate the sampling distributions based only on sample data. See you in 2 minutes.